Hi, today I'm going to talk about how to generate random sample from normal distribution, specifically bivariate normal distribution. So first of all, let's say we want to sample x and y from a normal standard distribution, and also x and y are independent, so that we can rewrite the function, a bivariate function, as the product of two normal univariate distribution, and also with mean 0 and sigma equal to 1. And then we can simplify this as our target distribution. And here we are going to use the Box-Muller transformation, so that we are going to let's say, rewrite the target distribution in another set of variables, and then we can do some sampling under this distribution, and then we convert it back to our target distribution under the variables that we want. So here we're going to use the polar coordinates. So as we should know that the polar coordinate is just the radius r squared is equal to x squared plus y squared, and then the theta, which is the angle, is just the arctangent of y over x. Okay. So now we are going to rewrite our target distribution under a new set of variables r and theta, so that here we are going to multiply by the 1 over determinant of the Jacobian, so that we can rewrite x and y into r and theta, where x and y is also a function. You can also write x and y as a function of r and theta, so that when you have r equal to a function of x and y, and then you can have x equal to a function of r and theta, so that you can you need to plug in the theta, or the function of r and theta, to the x and y here, and then multiply by the 1 over the determinant of the Jacobian, and then you can get your function in another set in the new variables. Okay, so now let's calculate the Jacobian here. So Jacobian is just basically your dr. So it's a matrix here, and then the matrix is written as dr dx as your first entry, and then your second entry on the first row is dr dy. So whenever you have one new variables, you can put them on your first row, and then take the derivative in respect to all your target variables. So you have dr dx and then dr dy. So that is your first row, and then your second row have your second new variables, which is theta. So your third entry on the in this matrix is d theta dx, and then your last entry is d theta dy. So that you have this is 2 by 2 matrix here, and basically just taking your new variables, taking the derivative with respect to your old variables here, and then you take the determinant of the Jacobian, which is the dr dx multiplied by d theta dy. So the diagonal. Take the diagonal and then minus the diagonal in the other direction, and then that's your determinant of the Jacobian. So maybe if you want, pause the video and try to create the Jacobian matrix by yourself, and then calculate the determinant, and also taking the derivative, and then try the determinant, just to verify or to see if I am also doing correctly. So that we have the determinant of the Jacobian, and now let's rewrite our target function in the new variables here, so that we have f of r and theta, dr d theta, which is 1 over 2 pi, which is the function that which is the formula we derive from here when we combine the two univariate normal distribution. And now we make sure we input that we put the Jacobian here. So our Jacobian is 1 over r, and then multiply by 1 over the determinant of the Jacobian, which is just r. So that we plug into here, and then we get our target distribution multiplied by the Jacobian, and then dr d theta. here I'm also going to do another transformation just to make our calculation or our later the sampling later make it more make it easier. So here I noticed that I have a exponential if you are familiar, then you will notice it looks like an exponential distribution, but not exactly. So to construct an exponential distribution here, we need to do some transformation. So we have a dr squared is equal to the 2r dr. So that is basically just taking a derivative, and then we move the 2 to the left hand side, and then we will have a which is the r dr can be rewrite as 1/2 of the dr squared. So we rewrite this part into our new variables. So now we are going to look in. So now our target function distribution is not under r and theta anymore. It's under r squared and theta. Okay. So and also here we rewrite the exponential part here, x squared plus y squared, and then we just change it to r squared. So here we have a function. Our final formula here is a function of r squared and theta here. Although there's no theta, well, 2 pi is the theta here, but there's no like a free variables here. So so basically what we are doing here is that we rewrite our target distribution from a variable x and y to the same target distribution but under new variables, which is first from r and theta, and now we convert it to r squared and theta. So that is, so let's compare with our previous formula here. We still have 1/2 pi multiplied by the exponential of negative r squared, where we have negative x squared and y squared. Here we just change it to r squared. So r squared over 2, and then multiply by 1/2, and then dr squared and d theta. So basically we are just changing the variable from x and y to r squared and theta. So now we can again we have independent relation between x and y, so that we can also separate our target distribution into the product of 2 other distributions. So you can notice that 1/2 pi basically just a uniform distribution over the interval from 0 to 2 pi, and then we also have this exponential negative r squared over 2, and then we also multiply by 1/2. So by changing the r dr to 1/2 dr squared, basically we are constructing exponential distribution with lambda equal to 1/2. Okay, so here let's break down this target distribution into 2 functions here, so that we have r theta, which is a function with only theta, one variables here, which is 1/2 pi. So that's so like I said, that's theta is a distribution of a random uniform. It's a uniform distribution over 0 and 2 pi. And also we have a function of r squared only. So f of r squared is 1/2 over multiplied by the exponential. So this function here, that means r squared is follow exponential distribution with a lambda equal 1/2. Okay, so now we have our 2 let's say variables that we can sample easier than just sampling let's say we use inverse CDF method, which can be very difficult, or there's no closed form solution for a normal distribution. So now we are going to use some easy some distribution that can be easily sampling from, and then we later convert it back to our target distribution. Okay, so for example here, let's say we generate 10,000 random sample for our for whatever need we have, and then we create a placeholder, and so here for each so theta basically is it's a uniform distribution. So we just basically do R unit. We do one sample, and then between the interval of 0 and 2 pi. Or if you want, you can also do 2 multiplied by pi, 2 pi multiplied by R unit, and then this is over the interval from 0 and 1. So, and then R is following exponential with lambda equal to 1/2, so that we can do a square root of R random exponential from with lambda equal 1/2, and then we want one sample here. Or if you want, you can we also talked about the inverse CDF method, where we use R unit to sampling from the exponential distribution, so that we can also use this formula here to sample exponential distribution from R uniform. But since as we all know, there's already a function in R that we can sample exponential distribution, so I'll just use that here. Or you can use either of these two to replace these two here, and then we convert it back to x and y. So basically, x is just r cosine theta, and y is just r sine theta. So that we do the algebra here to convert it back from theta and r back to x and y, and then the final result or the output for this algorithm here is your sample from your bivariate standard normal distribution. So now let's run the code here, and then we just generate 10,000 random sample from bivariate standard normal distribution. So although there are lots of built-in functions in R that you can do the same thing, but here I'm just going to talk about the logic or the algorithm behind this function here. So so sometimes we just like do one line code, and then we can get the same thing, but it will be more beneficial to learn what is exactly happening in the backend, or to have more knowledge about this, to appreciate the function here. Okay, so now we can plot our random sample. So in this graph, we have 10,000 dots here. So as you can see that it follows normal bivariate standard normal distribution. So that so all the dots is between -4 and +4, and then over this circle. So that means there isn't like a tilting angle here. So that means it is independent. And let's see if I can. So mean of x is negative, and then mean of y. So it's a very small, very close to 0. So so of course this is a random sampling. So it is not going to return exactly 0, unless the variant of x and then variant of y, so that you can see that it's very close to 1. So that means our function, our algorithm here is doing a good very good enough to generate a random bivariate standard normal from mu 0, and then sigma equal the sigma matrix equal to identity. So our algorithm is actually doing a pretty good job here. Okay, so we can also let's plot like a 3D graph here, so that you can see that it is very close to normal for the on these two variables here, from -4 to +4, and then look like a circle for the contour plot, and there's no covariance, so they're independent between x and y. Okay, so that is the algorithm like the long form of the logic or the algorithm to generate a bivariate standard normal distribution in generate random sample. And okay, so that is actually just a normal distribution, a zero and identity matrix. So now let's say we want to generate bivariate normal distribution, but with some mean and sigma, where let's say there is a covariance between they are not independent between x and y. So how we are going to do that in R? Okay. So here, x and y follow a normal distribution, but with x is with mean mu1, and y is actually with mean mu2. And here is their sigma matrix here. So here we have the covariance variance on the diagonal, and then their covariance on the other diagonal in this 2x2 matrix. So our goal or our method here is that we construct a new x here, which is equal to b plus a times z, where z is actually come from the normal standard bivariate standard normal distribution. And then we need to find b and a, and then after we find the b vector b and matrix a, and then we do this we construct this x, and this x should just follow this bivariate normal distribution with this mean vector and then sigma matrix here. Okay, so here, so let's say, we find the expectation of our new variables here, which is b plus a times z, and then we can see that our mu should be z. So our vector b should, we can just use mu to write our vector b. So here we find our vector b. So if we want to sample from a normal distribution with this mu, we can just construct these variables with b as this vector here. So this is what we want, and then this is what we're trying to construct, and then we find out that the b is already just the mean vector here. Okay, and now let's construct our A matrix here, matrix A. So our sigma matrix, which is just the covariance of X, and then we replace our new construction into over here, and then we just keep expanding. So the covariance of a constant term is 0, so that is covariance of A times Z, and then we put A matrix out. So the sigma matrix can be rewrite as A times covariance of Z and then times transpose of A. Since our Z is actually a standard normal, so that this become I, so that our sigma matrix can be rewrite as A times transpose A. So here we can use a decomposition to find A, which is called the Cholesky decomposition. So here we note that the sigma matrix is, well, of course, it's positive, and then it's positive definite. So we can use this Cholesky decomposition to find our matrix A. So our matrix A here is just upper lower triangular matrix here. You can use so you can construct our the matrix into this form, and then do A times transpose of A, and then you can make that equal to sigma matrix, and then you can do some algebra to find what is T1, T11, T12, T22 of this A matrix. So I already give the answer, but feel free to pause the video and then to derive it by yourself. So that T11 is just the sigma 1, and then here. So that if you use these three elements here to construct your A matrix, and then that A is, and then you find your A matrix A here, to construct your variable x here. So now we have find our vector b and matrix A to construct this, and then our new our target distribution will be can be found by using this construction. So let's say we want to generate random sample from a normal distribution with mu equal to 3, 4, which is the mean, and then our sigma matrix with this look like this. Okay, so you can see that, as you can see, there's covariance matrix. There's covariance between x and y. So it won't be like a perfect circle when we see in the graph. It will be like an ellipse with some angle tilting in the graph. Okay, so let's say we want to generate random bivariate normal distribution with this mu and sigma here. Okay, so now our what we need to do is to find a B and A, and then construct and then using a standard normal, bivariate standard normal, to construct our new variables here. Okay, so you can either use this by doing algebra to find the A matrix, or I will just use the built-in matrix, built-in function in R to find our matrix A here. So this is the Cholesky decomposition of sigma matrix, and that is our A matrix A here. So you can see that let's see if transpose of A multiplied by A here. So you can see. Oh, okay. It's already okay. Yeah. You can see that this is our So by multiply A transpose A, we get our sigma matrix back. So that means our decomposition is correct. So that is our matrix A here. So our new variable x is just mu plus A multiplied by z, where z is the standard bivariate standard normal distribution. Since we already get the normal bivariate standard normal from our previous example, and then I store it under x and y. So I will just borrow it over here to use it directly. So or you can use R-bind, I think R norm and then R norm here. You can achieve the same thing, but here I'm just going to emphasize that we can use our previous example here to generate that is normal distribution with mu and sigma here. So I just borrowed the standard normal we just created in the previous example here. So and here I construct our new variables here. So x is equal to mu plus A times z. So let's see. Our comean of the new variables here is 3 and 4. So that is our target. That is the mu for our target distribution. And let's take a look at the variance of our new variables. So that we have 1, 1 on the diagonal, and then 0.7 on the other diagonal. So that is our. So you can see that with this construction, we indeed find we indeed have the random sample with under normal distribution with this mu and sigma here, and then we can plot. So so here we have the same 10,000 dots in this graph, and then now you can see that there's like a well, it's not a perfect circle, it's an ellipse here. So that means there's some covariance between x and y. They're not independent. And then there's an angle tilting. It's not like a perfect circle, or it's not like a parallel to the axis. So that this is our this is 10,000 random sample from this target distribution here. And also plot our as you can see that there's like a angle here, or there's a spreading on the in this diagonal here. So that means x and y is not independent, and unlike the perfect circle. So this is how you can. So in summary, what we have done is that we use uniform distribution to sample from uniform distribution to get theta and r, and then we use theta and r, or r squared, converted back to x and y, and then we get our bivariate standard normal distribution. And then we use the standard normal distribution to get our generalized normal distribution with some mu and some sigma here. So in fact, of course, we can use like a one-line syntax or function to generate 10,000 sample directly from the computer. But actually, there is lots of things going on in the back end, and there are lots of math and calculation in order to achieve this amazing result. So feel free to pause the video and also try to derive the things by hand, and also verify it if I'm doing correctly or not. So thank you very much, and let me know if you have any question.